Welcome back, everybody. This is Mr. Johnson here with you once again. This is Lecture 17, Part 1, the quantum model. And then Lecture 17, Part 2 will be an extension of the quantum model into what is called electron configuration with some orbital diagrams in there. It is Wednesday, November 25th, the day before Thanksgiving, and I'd just like to share that I am thankful that as hard as this year has been, as challenging for us all as COVID has been, I'm thankful that we still get to learn chemistry together this year, and in my opinion are making the very best of it. In the last lecture, we talked about the Bohr model, how atoms can emit light as their electrons fall from higher energy states to lower energy states, and a little bit about the dual nature of light, that it exhibits both particle-like and wave-like properties, and that in fact all matter does. So we're going to start with a video that some of you saw already about Schrodinger's cat experiment and the dual nature of matter and light. If you've seen this, you can skip ahead to the end of this TED Talk, and I'll be back with you here in a moment.
Austrian physicist Erwin Schrodinger is one of the founders of quantum mechanics, but he's most famous for something he never actually did, a thought experiment involving a cat. He imagined taking a cat and placing it in a sealed box with a device that had a 50% chance of killing the cat in the next hour. At the end of that hour, he asked, what is the state of the cat? Common sense suggests that the cat is either alive or dead, but Schrodinger pointed out that according to quantum physics, at the instant before the box is opened, the cat is equal parts alive and dead at the same time. It's only when the box is opened that we see a single definite state. Until then, the cat is a blur of probability, half one thing and half the other. This seems absurd, which was Schrodinger's point. He found quantum physics so philosophically disturbing that he abandoned the theory he had helped make and turned to writing about biology. As absurd as it may seem, though, Schrodinger's cat is very real. In fact, it's essential. If it weren't possible for quantum objects to be in two states at once, the computer you're using to watch this couldn't exist. The quantum phenomenon of superposition is a consequence of the dual particle and wave nature of everything. In order for an object to have a wavelength, it must extend over some region of space, which means it occupies many positions at the same time. The wavelength of an object limited to a small region of space can't be perfectly defined, though, so it exists in many different wavelengths at the same time. We don't see these wave properties for everyday objects because the wavelength decreases as the momentum increases, and a cat is relatively big and heavy. If we took a single atom and blew it up to the size of the solar system, the wavelength of a cat running from a physicist would be as small as an atom within that solar system. That's far too small to detect, so we'll never see wave behavior from a cat. A tiny particle like an electron, though, can show dramatic evidence of its dual nature. If we shoot electrons, one at a time, at a set of two narrow slits cut in a barrier, each electron on the far side is detected at a single place at a specific instant, like a particle. But if you repeat this experiment many times, keeping track of all the individual detections, you'll see them trace out a pattern that's characteristic of wave behavior, a set of stripes, regions with many electrons separated by regions where there are none at all. Block one of the slits and the stripes go away. This shows that the pattern is a result of each electron going through both slits at the same time. A single electron isn't choosing to go left or right, but left and right simultaneously. This superposition of states also leads to modern technology. An electron near the nucleus of an atom exists in a spread-out wave-like orbit. Bring two atoms close together, and the electrons don't need to choose just one atom, but are shared between them. This is how some chemical bonds form. An electron in a molecule isn't on just atom A or atom B, but A plus B. As you add more atoms, the electrons spread out more, shared between vast numbers of atoms at the same time. The electrons in a solid aren't bound to a particular atom, but shared among all of them, extending over a large range of space. This gigantic superposition of states determines the ways electrons move through the material, whether it's a conductor, or an insulator, or a semiconductor. Understanding how electrons are shared among atoms allows us to precisely control the properties of semiconductor materials like silicon. Combining different semiconductors in the right way allows us to make transistors on a tiny scale, millions on a single computer chip. Those chips and their spread out electrons power the computer you're using to watch this video. An old joke says that the internet exists to allow the sharing of cat videos. At a very deep level, though, the internet owes its existence to an Austrian physicist and his imaginary cat.
All right, welcome back. So we're on page 291 of our ebook, or 283 of our textbook, and again we're in section 5.3, the quantum mechanical model of the atom. I'm going to read this first statement here in yellow to you, talking about the Bohr model, which is that Bohr assumed that for an atom there was only certain allowed energy levels in order to account for hydrogen's observed line spectrum. So based on the observations he made about these very specific colors, wavelengths, or energies of light being emitted by atoms, he proposed that electrons must exist in these distinct energy levels through which electrons are rising and falling. And he was correct, but he didn't have a theory for why. He didn't understand why. And it was the work of Schrodinger and Heisenberg and some other scientists who arrived at this dual nature of property theory, quantum mechanics, that was the explanation for why that is. So we'll talk about that here. These next several minutes are meant to be interesting and fascinating and reveal to you all of the crazy, wonderful things about nature. You're not meant to understand it, though, perfectly. So I want you to be okay with these next few minutes just being interesting and theoretical, but not making necessarily perfect sense. So we flipped our page, and we're looking at this image up here, which is a really powerful image. And it's comparing an instrument, a guitar, to how electrons move around an atom. If you're familiar with how a guitar works or other instruments work, they're designed in such a way that when you put your fingers on the frets or you play notes of an instrument, the waves, the sound waves, are standing waves. You get these harmonic frequencies that create stable sound waves and these nice sounds. When an instrument is working properly, you get these standing waves that have half wavelength integers associated with them. The same is true of electrons when they move around an atom. For an electron to not cascade into the nucleus, for an electron to have a fixed or stable amount of energy, the wavelength that those electrons assume as they move around the atom also have to create fixed waves or standing waves. Basically, the electron at some point has to return to the same place from which it began its journey. This image is a little misleading. It suggests once again that the electrons orbit in these circular or spherical regions, when in fact they don't. They move in these spaces called orbitals that we'll talk about. But within these orbitals, within which electrons have a fixed or distinct amount of energy, the electrons have a wavelength that allows them to create these standing waves or these fixed waves to return to the place from which they began. If an electron has a longer wavelength and therefore a lesser frequency or a lesser energy, those electrons, based on the way those standing waves work, are going to be closer to the nucleus. Electrons that have lower energy values, longer wavelengths, lesser frequencies are, on average, closer to the nucleus. Electrons with shorter wavelengths, with higher frequencies, with higher energies, we find will occupy orbitals or spaces that are, on average, a greater distance away from the nucleus, again, putting those electrons at a higher energy state. So while that may not have made perfect sense, and to me it still doesn't, although I can speak about it, that's meant to be a model for you or an explanation for you about why electrons can only be in certain allowable energy states or in certain fixed energy states. And again, it's based on the fact that they move in a wave-like pattern, and they've got to have a wavelength that gives them standing waves, and there's only certain wavelengths that achieve that, and it's only certain energies as well that achieve that. So I've skipped ahead a couple of pages. I'm on now 288 of the textbook, or 296 of the ebook. And although I'm not going to talk about this with you, I recommend that you read this little section called Seeing and Measuring. It's about the Heisenberg uncertainty principle, that we can never really know the location and momentum, or the location and speed of an object at the same time. Meanwhile, I am going to jump down here to this section about Schrodinger's equation, which is going to talk with us once more about these atomic orbitals. And what it says is the regions in which the highest probability of finding electrons, where we expect to find electrons in these standing waves, are called atomic orbitals. Atomic orbitals represent regions in a three-dimensional space around a nucleus where electrons with a particular energy are most likely to be found. We can view an orbital as a probability or a charge cloud, representing a 3D picture of where we will probably encounter the electrons around the nucleus. Now, to you could imagine that the electron is somewhere in that orbital, but be aware that these orbitals have electrons in them 90% of the time. The orbital describes the space around the nucleus where an electron is expected to be found about 90% of the time. And that's interesting, but doesn't need to be well understood. So the next segment of this video, after I reveal two more small things to you, is going to be looking at what these orbital shapes look like, where we expect to find these electrons 90% of the time when they're around the nucleus, and the energies that are associated with them, and how they all fit together in the quantum model, and ultimately allow us to do this thing called electron configuration, which describes where electrons are found. All right, the last thing I take you to is these 3 points of the quantum model, which are on page 289 of our textbook. And I'll read you them and talk you through them. So the 3 important aspects of the quantum mechanical view of the atom, the quantum model of the atom, that all of this is about and electron configurations are built on, are as follows. The energies of electrons in atoms are quantized, meaning they have a distinct amount of allowable energy. There's only certain allowable energy states because of their wave nature, because of this requirement for standing or fixed waves. This relates to the idea that only certain allowed energy states associated with standing electron waves can exist. So that's something that's meant to make vague sense. This second piece is about that little section, seeing and measuring, that I suggested you read. The Heisenberg uncertainty principle states that it is impossible to simultaneously state both where an electron is and where it's going, to know its location and its momentum. Finally, and that second part isn't as important to understand. Finally, atomic orbitals are those regions in three-dimensional space around a nucleus where electrons with a particular energy are most likely to be found. And once again, that's estimated to be at about 90%. And that's what we're going to talk about next, is what these orbitals look like. So we've jumped to section 5.4, which is on page 292 of your textbook, or 300 of your ebook, Applying Quantum Mechanics to Electrons and Atoms. I'm going to first talk with you about 4 different numbers that together describe the location of electrons. Each electron can be assigned 4 different numbers, 4 different quantum numbers. We don't actually need to know what the names of these numbers are, what letters are used to abbreviate them, but to me it's important that I talk with you about them and then simplify for you how it all comes together, what it all means. All right, so the first number that we assign to an electron around an atom is called the principal quantum number. The first quantum number is called the principal quantum number. It's abbreviated letter N, and it indicates the relative size of the atomic orbital. This number is analogous to the energy level number that Bohr used in his Bohr models. The first energy level would have a principal quantum number of 1, the second energy level a principal quantum number of 2, the third a 3. This is a number we will be referring to. We will refer repeatedly to the principal quantum number. These other ones a little bit less so. All right, let's skip to the next page. And the second quantum number, abbreviated with an L, is called the angular momentum quantum number. Besides this lecture, you may not hear me refer to that again. The second quantum number is related to the shape of the atomic orbital. I'll be showing you these shapes. We will be using letters to describe the shapes of orbitals as opposed to the second quantum number L, which range from -2 up to +2. We use letters. The letter S describes an orbital. There's an S orbital. There's a p orbital, and the p orbital has a certain shape associated with it. So the letter S, the letter P, the letter D, and the letter F are for us how we will describe the shapes of orbitals. Letters, S, P, D, and F. Hang on to those letters. All right, as we scroll down, the third quantum number, abbreviated M sub L, which we won't use in here, is called the magnetic quantum number, and it tells us the orientation in space of a given atomic orbital. We're just going to talk about how these orbitals exist on 90-degree axes relative to each other, and I'll talk with you about that in a bit. We refer to one p orbital as being on the p axis, another being on the y, another being on the x, rather than using this third quantum number. So orbitals exist in space relative to each other around an axis. All right, and the fourth quantum number is the spin quantum number, and I've skipped ahead to page 296 of the textbook. We'll go back to those other pages in a bit. Electrons also within an orbital that have a particular shape and size associated with them have a spin. And there's two spins that electrons can have, either positive or negative, or we could say clockwise or counterclockwise. And I'll talk more about that in a bit. All you need to know is that within the same orbital, electrons are spinning opposite to each other. One is clockwise, counterclockwise, positive, or negative. All right. So again, there's four things about these electrons we want to pay attention to. The energy level, the principal energy level they're in, the orbital they're in, the orientation of that orbital or of those orbitals around the nucleus, and then the spin that the electrons have. And I'll talk about all of that in a more, hopefully, logical or sensical way here in just a moment. So if you recall, I said there were four letters we used to describe orbitals or shapes of orbitals: S, P, D, and F. S orbitals are always spherically shaped. S orbitals are spherically shaped orbitals, and here is a reasonable representation of an S orbital. Each of those dots represents the different places that an electron could be found within an S orbital. But at any one moment in time, if there were only one electron in that orbital, we'd only see one dot. This is sort of a time lapse. Notice that the electrons are spending more time in the inner part of the S orbital than the outer part. And this outer edge sort of describes the region within which the electron could be found 90% of the time. S orbitals are spherically shaped. We'll talk at length more about that. P orbitals, and by the way, within an energy level, there is only one S orbital. Within a principal energy level, there's only one S orbital. I'll come back to that. P orbitals, on the other hand, are described as being hourglass, or peanut, or dumbbell shaped. People use different words for them. Hourglass, peanut, or dumbbell shaped. Each p orbital looks like an hourglass or a dumbbell. That is a p orbital. That isn't two p orbitals, but rather it's one. And there's two lobes to a p orbital. So this would describe a region where we'd expect to find an electron 90% of the time. Within a principal energy level, there are three p orbitals. There's one that lies on the x-axis, there's one that lies on the y-axis, and there's one that lies on the z-axis. If we superimpose all of these p orbitals on top of each other, we get what is called a p sublevel. A p sublevel contains the three p orbitals, all on different axes. And these are regions where we'd expect to find electrons 90% of the time. One thing I haven't said yet, but will be said repeatedly, is that each orbital, no matter what its shape or size, contains only only two electrons. A bit ago, you heard me say that each principal energy level only holds one s orbital. Therefore, the s orbital can only hold two electrons. The second principal energy level, which can hold three p orbitals, means that in a p sublevel, where there are three p orbitals, a total of 6 electrons can be found. A p sublevel can hold 6 electrons because it has 3 different orbitals that each hold 2 electrons. Again, this is all going to fit together here in a moment. As we scroll down, we see d orbitals, which kind of look like doubled up p orbitals. Looks like it's 2 hourglasses, 2 peanuts, 2 dumbbells. Notice there are 5 d orbitals within a sublevel. A d sublevel contains 5 d orbitals. And since each orbital, or each d orbital, can hold 2 electrons, a d sublevel can hold 10 electrons. A p sublevel, as we heard a bit ago, with only 3 orbitals, can only hold 6 electrons. And an s sublevel that only ever has one s orbital can only hold 2 electrons. An s sublevel with just one s orbital holds 2 electrons. A p sublevel with 3 p orbitals can hold 6 electrons. And again, a d sublevel with 5 d orbitals that are all on different axes relative to each other can hold 10 electrons. There's also an f sublevel, and we're not going to show you images of those orbitals because they get really crazy, but if you want to Google them, you can. There's a pattern here. Every sublevel has 2 more orbitals than the prior, and since the d sublevel had 5 orbitals, the f sublevel has 7. And again, since each orbital can hold 2 electrons, the f sublevel with 7 orbitals can hold 14 electrons. S, P, D, F. This is the first of 2 short videos I'm going to show you about orbitals, and this is just going to show us the shapes of orbitals, and the next one will show us them superimposed on top of each other for a particular element. This has got a hot soundtrack too, so sit back.
Orbitals.
So that was an s orbital, and notice that it was spherically shaped. There's only ever one s orbital, so we don't need to describe its orientation around the nucleus, because you could spin that sphere and it would still be in the same place as it was. Those are 3 p orbitals. That's a p orbital, that's a p orbital, and that's one. Together, they represent the p sublevel. The p sublevel, again, has 3 orbitals, and since each orbital can hold 2 electrons, this p sublevel can hold 6 electrons.
Orbitals.
Those were the 5 d orbitals that together represent the d sublevel that can hold up to 10 electrons, 5 times 2 being 10. And they weren't shown superimposed on top of each other because it becomes hard with d orbitals to see them all on top of each other as they occupy some of the same spaces as each other.
Orbitals.
But when they all are on top of each other, notice that the orbitals tend to occupy space that is unoccupied by other orbitals. Because, as you might imagine, electrons are all negatively charged and want to be as far away from each other as possible. In addition to being attracted to the nucleus and wanting to be close to the nucleus, in addition to having these wave functions that give them associated energy that keeps them from collapsing in the nucleus and assuming these really crazy shapes in nature. Why we think of atoms as being spherical is that the outer edges of all those orbitals, when superimposed on top of each other, do create overall a spherically shaped atom. So we are back to our book, of course. I'm on page 295 of the textbook, or 303 of the ebook. This is a really important diagram here. Flag this, highlight it, love it. Really important diagram. Okay, let's walk through this. What this is telling us is that in the first energy level, or the first principal energy level, there is just one sublevel. In the first principal energy level, there is just one sublevel, and it's called the S sublevel. An S sublevel only ever contains one orbital, an S orbital, that will be spherically shaped. And because this is an S orbital in the first energy level, it's a relatively small spherically shaped orbital. An electron in this orbital, or in this energy level, would be fairly close to the nucleus 90% of the time. There's only 2 electrons that can exist in that one S orbital. As such, the first energy level, like Bohr thought, can only contain 2 total electrons. And that's shown as well down here. The first energy level only has one orbital. It only has an S orbital. The second energy level has 2 sublevels, and they repeat themselves. There is an S sublevel and a P. All s sublevels only have one orbital, an s orbital that's spherically shaped. This one, though, would be a little bit bigger than the 1s orbital. The electrons in there have a higher energy state. There's also a p sublevel. All p sublevels can have up to 3 orbitals. The p sublevel contains 3 p orbitals, and those are hourglass or dumbbell or peanut shaped. With there being 3 p orbitals and 1 s orbital in the second energy level, because 6 electrons fit in a p sublevel and 2 fit into an s, that's why the second energy level, like Bohr predicted, can hold a maximum of 8 electrons. And that's shown down here as well. The second energy level has an s and a p. The third energy level, and there's a pattern here, has 3 sublevels, and the fourth, of course, has 4. The 3 sublevels in the third energy level are the 2 that repeat, an s and a p. The 3s sublevel would have 1 p orbital that'd be bigger than the 2p or the 2s or the 1s. It has a 3p. Those p orbitals are still hourglass dumbbell shaped on 3 different axes. They're just a bit bigger. And then there's the d sublevel with 5 d orbitals. And that d sublevel, again, can contain 10 electrons, 5 times 2 being 10. The third energy level can hold 18 electrons, 2 in the 3s, 6 in the 3p, 10 in the 3d, 18 total. And that's shown again down here. The 9 orbitals in the third energy level account for up to 18 electrons. The fourth energy level has 4 sublevels, an s, a p, a d. They have the number of orbitals we've already talked about. They're just bigger, these orbitals. And then there's also an f sublevel, which has up to 7 orbitals. 14 electrons can fit into the f sublevel. The fourth energy level can hold up to 32 electrons, 2 in the s, 6 in the p, 10 in the d, and 14 in the f. And again, that's shown down here. So I take you back to one last video so that we can see these orbitals superimposed on top of each other for an element scandium and start to see how the quantum model all fits together. So this is going to be a depiction of the quantum model for scandium with 21 electrons, and we're going to see the orbitals coming in one at a time in the order that electrons fill, from lowest energy state to highest energy state. Scandium's first 2 electrons go into the first energy level and into the 1s sublevel and into the one and only orbital in the 1s sublevel. So there would be 2 electrons inside of that 1s orbital. After the first energy level is full, we go to the second energy level. The lowest energy sublevel in the second energy level is the s. They always fill in order of s to p to d. If there's more than one sublevel in an energy level, that 2s sublevel only contains 1 orbital, a spherically shaped s orbital, so we'd see 2 more electrons in there. Now the 2p starts to fill. That's one of the 2p orbitals. Here comes another one. Each of those p orbitals can hold 2 electrons. Here comes the third one. Together they represent the p sublevel, so there's 6 more electrons that have been filled for scandium. 2 in the 1s, 2 in the 2s, 6 in the 2p, so we've accounted for 10 of scandium's 21 electrons so far. The second energy level is now full. It's full with a 2s and a 2p, so we're going to the third, and the 3s always fills first. After the 3s fills, the 3p starts to fill. In a bit, we'll talk about how 2 electrons don't go into the same orbital until all orbitals of a sublevel have at least 1 electron in them. Here are the 3p orbitals. So we're at 18 electrons right now. 2 in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, and 6 more in the 3p. So we're at 18 electrons. Now, something weird just happened, which is that the third energy level, which has a D, it has a S, a P, and a D, didn't finish filling. We went from the 3p to the 4s, and that's something we'll talk more about. After the 3p fills, the 3d does not fill. It fills out of order. After the 3p fills, the 4s fills, which is why we saw this 4s orbital coming in. And then we finish filling the third energy level and go to the 3d. So the very last orbital to fill is a 3d orbital that Scandium's 21st electron ends up in. So there is Scandium's quantum model, and the other d orbitals are flying in, although in Scandium's case, those other d orbitals don't have electrons in them. But they're beautiful to watch. That's it, folks. Lecture 17, Part 2, coming up next. We're going to apply our understanding of the quantum model to electron configuration, where things should start to get clearer, and from which we get this skill, which is to be able to write orbital diagrams and electron configurations. Thanks for hanging in there with me.